Hi everyone, in this video we are going to discuss bipartite graph. This is a continuation of our discussion of fundamentals of graph theory. To start, let's first define what a bipartite graph is. If the vertex set of a graph G can be split into two disjoint independent sets X and Y, then G is a bipartite graph. So a bipartite graph means two things. First, we can split the vertex set into two disjoint subsets, and these sets must be independent sets. So what does that mean? First, there exist two subsets X and Y of the vertex set V such that X union Y is V and X intersection Y is empty, meaning X and Y are partitions of the vertex set. We call X and Y the partites of the graph. Second, what do we mean by independent sets? Each edge of G joins a vertex of X and a vertex of Y. In other words, for every edge in G, one endpoint of that edge belongs to X and another endpoint belongs to Y. And no edge connects 2 points from X. Or similarly, no edge connects 2 points in Y. So no vertices in X are adjacent and no vertices in Y are adjacent as well. So every edge has endpoints, one coming from X and one coming from Y. This is an example of a bipartite graph. So the black vertices belongs to X while the white vertices belongs to Y. And every edge of the graph has endpoints, one from X and one from Y, and it does not have an edge consisting of endpoints from X only or endpoints from Y only. Vertices can be colored black and white such that each edge joins a black vertex which is in X and a white vertex which is in Y. So any bipartite graph can be drawn in such a way that one set of the vertices are colored black and one set of the vertices are colored white, and such that every edge has one endpoint colored black and one endpoint colored white. And no edge has both endpoints colored black or both endpoints colored white. So that's a bipartite graph. This is another example of bipartite graph. Although it is not drawn in the same manner, but we can draw the vertices either black or white in such a way that every edge will have two different endpoints, one black and one white. Let's say we start with this point and we draw it black. Then any edge incident to it must have at its other endpoint a vertex colored white. So these three edges are incident to the first vertex that we chose. So this must be colored white, and colored white. Now choosing one of the white vertices, let's say this one. So any other edges incident to it must have at the other endpoint of that edge a vertex colored black. So this is black. This should be black. And this is already colored black. So we're done with that. We continue this process of recoloring the vertices. So this vertex is colored black. So at the other end, it must be colored white. So these edges are both incident to this point and the other endpoint are white. So this must be black. And so we're able to color all the vertices either black or white. And we can see that no two blacks are adjacent, no two whites are adjacent, and all the edges has either one endpoint being black or one endpoint being white. So how do we make sure that this is indeed a bipartite graph? The best way is to redraw this in such a way that on one end, all vertices are colored black, and on the other end, all vertices are colored white. Of course, we already know that this is bipartite, and it's already enough that we were able to color the vertices either black and white, and it follow the requirement that any edge is colored black and white on each end, and no edges connects two blacks or two whites. So this is bipartite. But just to see that this can also be drawn in the same manner as our first graph, meaning one end are all blacks and the other group are all white vertices. So if we want to redraw this, so we will collect all the black vertices and the white vertices on each end. Now, this is a typical name of the vertices for Q3. So the vertices are entopoles with coordinate 0 or 1. So those are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. The black vertices are 0, 0, 0, 1, 1, 0, 0, 1, 1, and 1, 0, 1. The other four are white vertices. So let me redraw this cube. Now let me collect the vertices, the black vertices at the top. So let's say these are the black vertices. 1, 2, 3, 4. And these are the white vertices. 1, 2, 3, 4. And then I have here vertex 0, 0, 0, 0, 1, 1, 1, 0, 1, and the other black vertex is 1, 1, 0. On the other hand, the white vertices are 0, 0, 1, and then 1, 1, 1, and then 1, 0, 0, and 0, 1, 0. This vertex here is connected to three vertices 0, 0, 1, 0, 1, 0, and 1, 0, 0. So these are the vertices 0, 0, 1, 0, 1, 0, and 1, 0, 0. There. Next vertex 0, 1, 1 is connected to 0, 0, 1, 1, 1, 1, and 0, 1, 0. Next, this vertex 1, 0, 1 is connected to 0, 0, 1, 1, 1, 1, 1, 0, 0. And finally, this vertex here is connected to 0, 1, 0, 1, 1, 1, and 1, 0, 0. So, in this representation of Q3, we can easily see that one set X composing of 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0 are independent, meaning there's no edge connecting any two of its vertices. And the other set Y is composed of 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 1, 0. Also, no two vertices in Y are adjacent. So the set X and Y are partitions of the vertex set, meaning X union Y is B. X and Y are disjoint, and any of the edges in G has endpoints 1 from X and 1 from Y. So that's what we mean by bipartite graph. Now, a complete bipartite graph is a bipartite graph in which each vertex in X is joined to each vertex in Y by just one edge. We denote by KRS a complete bipartite graph with the number of vertices in X equals to R and the number of vertices in Y equals to S. In our previous example of bipartite graph, it doesn't necessarily have to be adjacent to all of the vertices on the other end. For instance, on our cube, 0, 0, 1 is connected to exactly 3 of the vertices. And any of the vertices of X are connected to exactly 3 of the vertices on the other set. But for a complete bipartite graph, any point on one set must be connected to each vertex on the other set. So if R is the number of vertices on X and S is the number of vertices on Y, then we denote this by K sub R comma S. These are the few examples of complete bipartite graph. So this has one vertex on the first set and two vertex on the second set. So this is K12. This is K13, one black and three whites. So if you want to draw it the same manner as a bipartite graph, so we can draw this black at the top and three whites at the bottom. So that's your K13. This is K22. We have two blacks and two whites. If you want, we can draw this way. This is two blacks and two whites. So these two blacks is connected to two whites, and these two blacks is also connected to two white. This is K23. We have the two blacks here and the three whites here. You can also draw that this way. So let's say you have two blacks and three whites. So every black is connected to white. Every black is connected to white. And every white is connected to blacks. This is K33. Take note that there is no vertex in the center of the hexagon. So we have three blocks here. And then the whites. So you can also draw that this way. You have three blacks and three whites. So as you can see, all the blacks are connected to the whites. And all the whites are connected to the black. So that's what we mean by a complete bipartite graph. So all you need to do to make it complete is you need to connect all the black vertices to each of the white vertices. And all the white vertices, of course, must be connected as well to each of the black vertices. Now, each black in X is connected to all the vertices in Y, and each white in Y is connected to all the black in X. So to write that in set notation, that would imply that the vertex set is partitioned into X and Y, meaning X union Y is the vertex set, X intersection Y is empty, and the edges are composed of all edge XY, where X is an arbitrary vertex in X and small y is an arbitrary vertex in the partition Y. Now, this is a very nice property for graph. Every closed add walk contains an add cycle. So, what do we mean by an closed add walk? So, you make a walk which contains of add edges such that the first vertex is the same as the terminal vertex. So, you just make a walk in your graph until you reach the starting point. Okay? So we prove by induction on the length L of a closed add walk. So what is a walk of length 1? If it is of length 1, then it must be a self loop. So we have a vertex and then you make a loop. So the length of that walk is just 1. Now, what is a walk of length 3? So if you make a walk of length 3, either you can make a walk on 3 distinct vertices, or you can make a walk on parallel edges. A walk of length 3 on 2 distinct vertices. So that means you must have a parallel edge, and then you have a loop here, and then on the other end of the parallel edges. Or you can have just one vertex and make 3 loops. So that will still comprise of a walk. Now, in any of these possibilities, you can always form an odd cycle. So this is a cycle with length 3. This is a cycle of length 1, and this is a cycle of length 1. Same as a south loop. This is a cycle of length 1. So anytime you have a closed odd walk, each walk contains an odd cycle. So for the basis of our induction, we're able to show that yes, it is true when the length of the closed odd walk is 1, as well as when the length of the closed odd walk is 3. So let's assume that for a closed odd walk of length L, where L is an odd number, any closed odd walk shorter than L contains an odd cycle. So we must be able to show that that walk also contains an odd cycle. Now, if W has no repeated vertices other than the first and the last, then W itself is an odd cycle, right? So we're done with that part. Now, what if, on the other hand, you have a repeated vertex? So let's say you make a walk. Let's say you start here, you make a walk until you return here again. But by doing so, you repeat a particular vertex. Let's say this vertex here is repeated. It could be the only repeated vertex. It could be one of the repeated vertex. So all we need to do is to choose any of the repeated vertex. So let's say this is a repeated vertex. So what you can do is you can rewalk your previous walk, but this time you're starting at the common vertex V. So we can start a walk from V on one side. So meaning you can split this walk, right? You can walk that path or that trail until you reach here. So that's one walk. And then you continue the other part of your walk. Let's say this part right here. And this is another walk. So if there's a common vertex, you can split your walk into two different closed walks. Walk 1 and walk 2. Now, both of these are closed walk. And each of them is shorter than the original walk, right? Because you split the original walk into two. So what happens is that since the original walk has odd number of length, then if you split that into two, then that would imply that one of the walks must be odd and one of the walks must be even, right? So they cannot be both odd or they cannot be both even. Definitely one of them will be odd. Without loss of generality, let's say W1 is odd. So since W1 is an odd closed walk, which is of length shorter than L, shorter than the length of W, then by hypothesis, W1 must contain an odd cycle, right? Because it's a closed odd walk shorter than L. Actually, in our illustration, this is the odd cycle that we're looking for. So this is an odd cycle. And that will always happen if you have an odd walk or a closed odd walk. So that's what happens. Since W is of odd length, one of this walk is odd. And since that odd walk is shorter than L by hypothesis that odd walk must contain an odd cycle. So that completes our proof. Now, this is a very nice theorem for us to determine whether a graph is bipartite or not. A graph is bipartite if and only if it has no odd cycle. Now, we have a way to determine whether a graph is bipartite or not. So, if it's bipartite, then it cannot have an odd cycle. If it has an odd cycle, then it cannot be bipartite. So, this is a very strong theorem in determining whether a graph is bipartite or not. So let's prove this. So since this is biconditional, we need to prove the necessary and the sufficient condition. So first, we suppose that the graph G is bipartite, then we show that it has no odd cycle. Next, we assume that it has no odd cycle, then we show that the graph is bipartite. So let's start with the first implication. Let G be a bipartite graph. So imagine if you have a bipartite graph. So let's say that's our bipartite graph. And you want to make a walk. So every walk in G alternates between two vertices, right? So let's say you start with this one. So if this is our X partite and this is our Y partite, so every time I make a walk on an edge, you alternate from X to Y. You start from X, then you go to Y. From Y, you go to X. From X, you go to Y. From Y, you go to X and so on. That's what happens when we make a walk in G. We alternate between the two partites. So, if you need to make a cycle, since this is a closed walk, then you need to return to the original set. Meaning, if I start with U, then I need to go back to U again. So, in order to do that, the number of edges is always even. So every return to the original partite happens after an even number of steps. Hence, you cannot have an odd cycle. Now, let G be a graph with no odd cycle. So we want to prove that G is bipartite by constructing a bipartition of each of the non-trivial components. Of course, any isolated vertices may belong to any of the partition. So meaning if you have isolated vertices, you can just add that to our partitions X or partition Y, and it will not really matter in our partition since there are no edges connected to that isolated vertex. So all we need to do is to partition every non-trivial component. Okay? So let H be a non-trivial component of G, meaning H itself is a connected graph. And let U be a fixed vertex on H. Now, for each vertex in H, define f of B as the minimum length of a UB path. Let's say we have a fixed point U. And then we have another vertex B in each. So you get all the possible path from U to B. So what is f of B? F of B will be the minimum length of a UB path. So all you need to do is to get the minimal path from U to B, or that means the shortest possible path from U to B, and you get the length of that path. That is always defined since H is connected. So there's always a path from U to B. Just get the shortest path, and the length of that path will give you the value of f of b. So for example, in this particular instance, suppose that this is the shortest path from U to B, then f of b is 4. So now we construct X to consist of all vertices X such that f of X is even, and Y to consist of all vertices Y such that f of Y is odd. Let's have a picture so that we can understand it clearly. So suppose that this is part of our graph. Now starting from U, any other point on H must be connected to U. So there is always a path from U to any point or any vertices in H. So let's say H has other vertices A, B, C, D. So if we take a look at this graph, there's an edge connecting U and A, right? There's an edge connecting U and B, and then B is connected by an edge to C, and C is connected by an edge to D. So if we want to get f of U, since U requires a path of length 0 to get from U to U, then f of U is 0. So U belongs to X because 0 is even. Now, both A and B is adjacent to U. So, exactly a path of length 1 connects U to A and U to B respectively. So, that means f of A and f of B are both equal to 1. So, both A and B belongs to Y because 1 is odd. C connects U by a path of length 2. U to B, then B to C. So that means f of C is equal to 2, which is even. So C belongs to X. D is connected to U by the path U to B, B to C, C to D, which is of length 3. We're assuming that that's the shortest path possible to reach D from U. So that means f of D is equal to 3, which is odd. So D belongs to Y. So for every point in H, we compute f of V. Now, if f of B is even, V will belong to X. But if f of B is odd, that vertex will belong to Y. So any of the vertices belongs either to X or to Y, but not on both. So that means X and Y are disjoint. Now, if you get the union of all these points, of course, X union Y will be H. So, X and Y satisfy our first requirement for a partite, that these two sets are disjoint. So, all we need to show now is that this set is independent as well. Meaning, no two vertices within X or within Y are adjacent. Now, suppose that that is not the case. Suppose that there is an edge within X or within Y. So, what will happen? So, let's say we have two vertices here, V and V prime. And let's say that there's an edge connecting V and V prime in our graph. So, what does that mean? Now, observe that since our component is connected, then there must be a path from U to V, right? There should be a path from U to B. Now, according to our construction, the path must be of even length if they are in X. So, let's say we have this path going to V and V prime as well. Let's say we have this path going to B prime. So, if both V and V prime belongs to X, then that path are both even. So, even plus even is an even length if you connect those two paths, the V prime path and the V path. Now, what if both V and V prime are in Y? So, that means the path from U must be odd, right? But if both of them are odd, the path from V prime U and VU are both odd, then adding those two would mean an even length. So no matter where you place the edge, either within X or within Y, the sum of those paths will still remain even because they are either both odd or both even, right? And then if V and V prime is an edge, then you were able to make a closed walk in our graph starting from V, go to V prime, and then from B prime, go to U using the UB prime path, and then from U, go to B using the UB path. So you were able to make a closed walk, but observe that since V prime U path and UV path together is always an even length, plus the edge VV prime makes our walk a closed ad walk, right? So that will make our walk a closed ad walk. So whenever we have an edge, either within X or within Y, we can always create a closed ad walk using the UV path, the UV prime path, and the edge VV prime. That's already a contradiction. Why? By lemma, W must contain an add cycle because it's a closed ad walk. So sabi ni lemma, basta may closed ad walk ka, lagi kang may add cycle. But this will contradict our hypothesis. Bakit? Sabi natin sa hypothesis, di ba, the graph contains no add cycle. So that means the edge VV prime does not exist. So X and Y are independent sets. That means H is a bipartite component of G. So if you have any component of G, you can always form its bipartition and then you just compose your G as the collection of your bipartite components. So that makes G bipartite as well. As I said a while ago, this is a very strong theorem because this makes our search for bipartite a lot easier. To prove that G is not bipartite, all you need to do is to find an odd cycle. Because once an odd cycle exists in a graph, then by this theorem, we are sure that this graph is not bipartite. On the other hand, if you wish to show that G is bipartite, then all you need to do is to find a partition of G and show that the two sets are independent, meaning no vertices within each partite. Okay. We can actually extend the definition of bipartite in general. So let R greater than or equal to 2 be an integer. A graph G is called an R-Partite if V admits a partition into R independent subset. So here, instead of just two partitions, we're now looking at R partitions. So R independent subsets. So again, the second requirement is that these are independent subsets, meaning no edge of G within the same partite. So if x1, x2 up to xr are partitions of V, then we must have V is the union of x1 up to xr, and xi and xj are disjoint or the intersection is empty whenever I is not equal to j. That's the first condition. The second condition is that each edge of G joins two vertices of different partites. So you cannot have an edge within the same partite. So this is an example of an R-partite where R is equal to 3. X1 composed of these three vertices. X2 is these two vertices and X3 is this one vertex. So as you can see, no two vertex within the same partite are connected and any of the edges connects one vertex from a partite and another vertex of the other partite. So you can also use our different colors for the vertices such that no edge join two vertices of the same color. So basically, the same with the idea of a bipartite wherein we use the color black or white. So in this case, if it's an R-partite, then we use R different colors to color the vertices. All we need to do is to make sure that every edge has two different color for endpoints. Now, an R-partite graph in which every two vertices from different partition are adjacent is called a complete R-partite graph. Remember, in our complete bipartite graph, we connect every vertices from X to each vertices from Y. Now, in an R-Partite graph, in general, what we do is we connect every vertices of a specific partite to all of the vertices of the other partites. Now, if x1, x2, up to xr are the partites such that the number of vertices in x sub I is equal to n sub I, then we denote the complete R-Partite given by k sub n1, comma n2, comma n3, and so on up to nr. So this is just a generalization of our bipartite. So instead of talking of just two vertices or two subsets of vertices, we are talking of R subsets of vertices. Now, the subscript denote the number of vertices in each partition. So, for example, if we want to take a look of K2 to 2, so that means we have two vertices on each partition. So, we have three partition with two vertices, and two vertices. So, all we need to do is every edge here connects two vertices coming from two different partitions. So, let's say, let's take this first partition. So the vertex here must be connected to every point in the other partition. So that must be connected to these two vertices of x2 and two vertices of x3. So we connect this one and this one. So we don't connect it to any of the vertices within the same partite. Now for the other vertex, we do the same. We connect to every vertices on the other partites. So that completes the edges coming from x1. Now from x2, since all the vertices of x2 are connected to all the vertices x1, all we need to do is to connect it to x3. So we add these edges and these edges as well. Now on the last partition, we already know that all the connections from the first two partitions were already made. So no edges may be added further coming from X3. So that's what a K222 looks like. Now what if we want K sub 1313, meaning we have four partitions. One partition has one vertex, the other has three vertices, another has one vertex, and the other has three vertices. So that would require this. So let's say this is the first partition, this is the second partition, the third partition, and the fourth partition. So we connect the vertex on the first partition to all other vertices. Now x2 is already connected to the vertices of x1. So all we need to do is to connect this to the vertices of x3 and x4. Next, x3 is already connected to the vertices of x1 and x2. So all we need to do is to connect this to vertices of x4. Finally, we no longer need to connect any of the vertices of x4 since it's already connected to each and every vertices of partitions x1, x2, and x3. So that's our K1313. Of course, it doesn't matter which partition you choose as x1 or x2 as x3. So that would still form the same graph. So meaning this is the same graph as K1133 or K3113 or 3313. It doesn't matter where you which partition you take first.